is equal to a mass times an acceleration. Now, forces are also equal to mv squared over r for an object moving in circular motion. Now, a force is equal to a third equation, g, capital M, lowercase m, over r squared. Now, this force is for an object that's orbiting around another object. This force is for also circular motion, an object orbiting around another object. This is a force that we can set equal to another force. If this force is equal to this, and this force is equal to this, then this is equal to this. So we're going to set these two equal to each other. mv squared over r is equal to g m over r squared. Now, we're going to go ahead and cross multiply and get rid of the fractions. So we have mv squared r squared is equal to g m times r. Now, v squared in circular motion, let's look at that. Distance is equal to velocity times time. Velocity is equal to a distance over a time. The distance in circular motion is equal to the circumference, so that's 2 pi r, and the time is called the period, so that's a capital T. We're going to substitute what the velocity in circular motion is equal to in here, and that's going to be squared, so 2 pi r over the period squared times r squared is equal to g m r. This is going to be 4 pi squared r squared over t squared times m times r squared is equal to g m r. We're going to divide by r and then multiply these. We're going to be left with 4 pi squared r cubed m over t squared is equal to g m. The next step, we can divide by the small masses. So we're left with the mass of the primary body. So this would be the mass of the sun, and this would be like the mass of a planet around the sun. Or this would be the mass of the Earth, and that would be the mass of the moon. So the secondary mass that's orbiting around a primary mass. This would be the radius of the orbit, or the distance that one object is orbiting around the other object. And that would be the time that it takes for one complete orbit or rotation around. So we're going to divide by the smaller mass object, moon or planet, and that ends up not mattering any longer. So 4 pi squared r cubed divided by the period squared is equal to g m. Now, if we divide by 4 pi squared, we're left with the radius cubed over the period cubed. So we end up with r cubed over t squared is equal to g m over 4 pi squared. This is usually shown as t squared over r cubed, so I'm going to flip everything. And basically what you do is you multiply t squared, you multiply by 4 pi squared, you divide by r cubed, you divide by gm. So this is going to end up being t squared over r cubed is equal to 4 pi squared over gm. That's normally how it's seen. And if this is what the period and the radius of the planet's orbit are equal to, related to the larger mass, if we apply that to a system, then every planet, every small planet in the system, orbits at something equal to this. Now let me explain that a little better. Let's say that you have the sun here, and this planet is orbiting around the sun. This planet is also orbiting around the sun. Well, this part of the equation is going to be the same no matter what planet you're dealing with. So we can say that the period squared of the first planet divided by the orbital radius cubed of the first planet is equal to the period squared of the second planet divided by the radius cubed of the second planet. So without even having any information about the mass of the sun at all, Kepler determined that if you knew the period and the radius of one planet and the radius of another planet, you could calculate the period that the other planet orbited around the sun. Or one of these variables would be missing, and you could figure out what that one variable was equal to.